Next up, we have EM number 7, kind of like a part 2. And here we're going to be describing not electric potential energy, not even electric potential, but electric potential difference. So this is when a charge moves location in an electric field the electric potential changes. And what this is really getting at is that the energy is changing. We just have all these kind of fancy words that all look alike. So it can be confusing, but I hope that we're kind of understanding. But electrical potential difference is kind of like the change in electric potential. So we actually call that delta V. So before we had electric potential, and now since we're having electric potential difference, there must be a kind of difference. It must have moved, which is kind of the definition. It moves the location, and the electric potential changes. So we have a change in electric potential, which comes from a change, it kind of means that there's a initial amount of volts and a final amount of volts. And like any change, we subtract final minus, we do final minus initial. The other way to kind of look at this is that the change in electric potential is going to be the change in electric potential energy divided by the charge that moved in the first place. This is often referred to as voltage. And so it's measured in volts. It's just a bit of a different concept. We want to make a note that one of the units that we'll be using is called the electron volt. So the electron volt is an energy. So the electron volt is energy, is an energy that an electron gains or loses when passing through a voltage of 1 volt. So when delta V is equal to 1 volt, if a charge were to move location in that, it would gain or lose an energy that we refer to as an electron volt. So we can kind of rearrange and solve for that energy. We have 1 volt is equal to delta EP over the charge of an electron, which is 1.6 times 10 to the negative 19 coulombs. This allows us to say that the energy, the change in energy for this electron would be 1.6 times 10 to the negative 19 joules. This energy, 1.6 times 10 to the negative 19 joules, is referred to as 1 electron volt. Okay, so now let's take a look at one of the only places where we can kind of apply all of this, and that's our parallel plate setup. So we'll draw our two ends of the plates, positively charged and negatively charged, and I have mentioned before that this is a uniform electric field. So we have our electric field, and here we get to say that the work done is equal to the force multiplied by delta D. And you can kind of always say that. However, we also want to look at the idea that you have the electric field, which is equal to the force divided by the charge. So, therefore, force is equal to EQ. So that is our first substitution that we'll make. We'll say that the work done is actually equal to the electric field multiplied by the charge. So got to remember to put our arrow overhead, multiplied by delta D. Now, here we can also say that the work is equal to the change in energy because it's a uniform electric field, and so that's our next step in this derivation. Finally, we have a second substitution, and that's that the change in electrical potential divided by Q is equal to delta V. So, oh, I forgot my Q here. EQ delta D. So, as quickly as we put it in there, we're actually going to divide both sides by Q because we're allowed to do that. And this will cancel here, but I'll have created delta EP over Q. So I can substitute this thing here with delta V is equal to the electric field multiplied by delta D. And that's kind of the whole culmination of the last few topics, which is that the electric field between two parallel plates is represented by the voltage divided by the distance. So that distance being how separated the plates are. This is pretty key. It finally gives us a way to calculate something for the electric field based on voltage and separation of the plates, or calculate something like the voltage based on the electric field strength. This is kind of one of the first equations we've seen in a while to start to relate some of the things that we've talked about. It's also worth noting that this electric field can be thought of as 1 volt per meter. 1 volt per meter. And a volt was also considered to be a joule per coulomb. That's what we saw in the last kind of couple of pages ago. So a volt was a joule per coulomb because it has to do with electrical potential per charge. Electrical potential, energy for charge. So then we can also make the jump that a joule is a Newton multiplied by a meter. So a joule per coulomb is a joule per coulomb over meters. Now I've got meters on top, meters on the bottom, so I can cancel this, and I can end up with 1 this should be a C. Right, because it's a joule per coulomb per meter, and a joule is a Newton per meter, so it's a joule per coulomb per meter. And so therefore we have Newton per coulomb. Beginning to realize that you probably couldn't see much of that, so let's do it over here one more time. Hopefully it makes a little more sense. So this is a volt per meter. So volt per meter. A volt, as we saw, was 1 joule per coulomb. That's also, so volt per meter. A joule is a Newton meter. So joule per coulomb per meter. This cancels, and we get a Newton per coulomb. So these two things are equivalent. So it's good to note that 1 volt per meter is also the same as 1 Newton per coulomb.